Hi, Subhash. Hi, Rakesh Kumar. Hi, Josh. Hi, Luis. Good morning, Subhash. All right, we're still waiting another minute. And this is also not a bad time to download. So there should have been a new instance of the slides and the code put up. So the code, I did add some stuff to it this morning. So you want to make sure that if you tried to download the code before like 20 minutes ago, that you download the most recent version. Hi, Francisco. Hi, Ira. All right, so today we are going to be covering the first part of two parts on probability and statistics. So we have a second session that is going to be on Thursday, where we'll continue with the probability and statistics. Was week 4 code and slides updated? Program support. Do you know if the week 4, for some reason, hold on, I'm just going through. For some reason, I feel like data viz. Okay. Oh, so Danielle is on, right? And Steve, so they're saying that the week 4 code and slides were uploaded. Okay, so now that it is a couple minutes after 11, we can start. So we're going to be talking about probability and statistics. Sometimes it's difficult, especially when we're trying to cover a lot of material in a very short time, to really break them out into 2 subjects. But basically, probability is logically self-contained. There's a single correct answer. And so what does that mean, right? We've heard about, the bell curve. There is a formula that creates that bell curve. And so we can do mathematical calculations based on that, right? So those types of things, if we roll a die, there's 6 sides. We know that the probability is 1/6 of each side. But in statistics, we're working with actual data. So there's uncertainty there. And so sometimes our data will approximate a normal distribution, or we could roll a die, but we're not, when we roll a die, we're not necessarily going to get 1/6 of each side, right? It's a random process. And so when we extend that, and we're working with data, there's uncertainty, and we have to utilize experiments, and we can utilize simulations, and we can utilize ideas from probability to help us answer questions with statistics. But in statistics, we are collecting data. It may follow forms that we see in probability, but with probability, there is a closed solution set. We have functions, we can calculate it. And in statistics, we're working with data. And so although we expect that if, we're at roulette and we're betting on black, we expect it to come up 50% of the time. Really, we could have a string of, red coming up 20 times in a row, even though that's improbable, it is possible. And so, there's differences there, but they are very closely related. And so it makes sense to cover both of them together. And so, yeah, we're going to try to do our best with the limited time that we have to cover a good amount of probability and statistics. So because of that, we're going to be narrowing down to just a couple important topics that are really going to relate to when we're later in the course, when we're building linear regression and logistic regression models, that you'll understand what a t-statistic is, a p-value, confidence intervals. So we're going to be talking about those types of things. But a lot of that is going to be next week, that we're talking about the confidence intervals and p-values. But to get to that point, we're going to today be talking about sampling and random variables and probability distributions. So namely the normal distribution, the t-distribution, and the Bernoulli distribution. Okay, so sampling. A population, right, is the total of a certain group of people. So an example of that would be all women aged 25 to 30 in Iowa. So if we, if we gave a survey and got a response from every woman aged 25 to 30 in Iowa, we'd have the whole population, right? But often surveying costs money. So we take a sample and we want to be representative. So we do a sample size calculation. But the idea is we have a total population, and often we're working with just a small piece of that population, and that is our sample. So the sample might be choosing 5,000 women from the total population of all women aged 25 to 30 in Iowa. So the sample is always less than the population total, because if it was equal to, then it would just be the population. We are going to now talk about two different sampling methods that you'll use in, and support. Do you see that Danielle is asking for a panelist link? Wanted to make sure you saw that. So we're going to cover simple random samples and stratified random samples, because they are the two that I use most often in my data science work. Also, I'm sure that you're familiar with the idea of building out testing, training, and validation sets, or just testing and training sets for model building. Maybe you've never heard of it before, but that's how we do machine learning, is we randomly separate our data into two groups so that we can build a model on one and then see how its accuracy is on the other data set. And that's supposed to give us insight into how well would this model work if it now sees data that it hadn't seen before, right? And so we can artificially create that scenario by building the model on the training data and then testing it on the testing data that the model hasn't seen before. Okay, so the two methods of sampling that we're going to cover are called simple random sampling and stratified random sampling. Okay, so simple random sample is what you'd think about probably when you hear the term sample. We have a population, and each member in that population has the same probability of being chosen. And so in the business context, what we're typically talking about is we have millions of rows of data. It would take a ton of time if we wanted to build these computations that we wanted to do on that million rows of data. So we're going to sample, 1% or 5% of the data and do an analysis that way. And when we have tons of data like that, often we're just going to take a simple random sample of like 1% of the data, or we'll say we want 50,000 rows, 100,000 rows. It really depends on the context of what we're doing. If we're going to build a model with a ton of different variables, well then, we'd need a larger sample because some of the effects in some of the variables might be smaller, right? And so these are all considerations that we need to take into consideration. But in general, a simple random sample is the idea that each row of data or each member in our population has the same probability, the same chance of being included in the sample that we're going to pull, right? And so this is the type of sample that we're using often when we create our testing and training splits for modeling. Sometimes you'll hear, sampling being presented as like, what do we do when we don't have all the data? Well, no, sometimes we have all the data, but it would be really computationally intensive and not necessary to use all that data, right? Because if we can take a sample and have the same accuracy or similar accuracy as if we were using the population, well, we can save ourselves the some of the computational complexity, right? Another area where I've used a simple random sample in industry is when I've done an analysis and there are companies that sell data about people, and so if you have people's names and hi Madhu. So technically it's not purely random, but the R has built-in functions that allow the randomness to be close enough, but that's like a deeply theoretical question. And then the way that you check to make sure that your sample is sufficient is you see if there's any bias in the variables between, like if I was dealing with internal data in a company, I might take a sample of 50,000 and say, okay, what's the distribution here of the variables that I care about? Is it similar to the distribution of the variables of the population before I move forward and check that my sample is actually representative of the population? So there is, oh, and Madhu, yeah, you have all panelists. You need to make sure that you change your thing to say all panelists and attendees so that other people can see your question. Okay, and Madhu's question was, how is it possible that each member has the same possibility of being chosen? How is it ensured, right? And so then, even if people is a rough, this is like a theoretical example, because obviously if we chose people to participate in something, in the case where we're dealing with people, often they're not going to complete our survey, or they're not going to answer the phone, or even if we were to knock on their door, they might not be home. And then bias is introduced, right? Because if the people who are likely to not be home at certain times of the day, they might share certain characteristics. There's all sorts of ways in which response bias can be introduced. So But the idea is that we are using the computer to draw a random sample from a population, which is the data that we have in our database or in the data set. And we're able to use that for our analysis. Okay, so sampling error can occur with a simple random sample, which is what we were just talking about. So it is possible that, you know, even with a large amount of data, you could still take a sample from your data and it doesn't accurately represent what is in the population. Now, there are different theorems, probability theorems, that ensure sort of, for the most part, it is going to work, especially if your data is large. But you may want to check, especially for variables where if it's like, you know, the tail end of people's spend, you know, people with high spend or whatever, it depends on what you care about. But in general, this is going to work pretty well. And so just to show you how, Francisco, we're getting there. Okay, so if we go over to our code for the day, if you don't have, so CA Tools is a library for creating, testing, and training splits. And so we'll want to load these different packages. So we're really familiar with dplyr. We're really familiar with ggplot2 from our lectures with Danielle. And then CA Tools allows us to create testing and training splits when we're model building. And that's a great demonstration for today where we're talking about sampling. And then our lab is just once we get into talking about generating random data from a probability distribution. This allows us to get it from the Bernoulli. Okay, so we need to pull in our data. We're just going to be using the CAR data set today. It is it should be available on Canvas for you. And program support, Danielle is still looking for panelist access. Okay, so this data only has 301 observations and 9 variables. We can look at the structure. Okay, and so we see that we have the name of the car, which is of course a factor variable. We have the year, the price that it's sold for, the present price, how many kilometers driven, and so the selling price is in thousands. Whether it's diesel or some other fuel type, who the seller was, whether it was a dealer or they sold it individually, and then whether the transmission is automatic or manual, and how many previous owners they've had. Oh. Let's see. So Lara is asking if there is a way to make the font bigger, and there is. I just don't remember what it is. Is that better, Lara? Okay, great. Okay, so hi Francisco, did you install it first? So you might need to go to packages, install. RLab. Okay. And so the first thing we're going to do is set seed, and this ensures reproducibility, which is incredibly important because we want the person who takes a sample after us, or maybe somebody wants to rerun our code, we want to make sure that that person can get the same exact result that we got. And so you need to set seed before every single thing you run that'll need it. So if I run a model and then I rerun a model, I will run the same seed both times if I want to apply the seed to that model. So every time I run a function, I will need to rerun set seed if I plan on using set, if there's any randomness involved in that function. Okay, so if we all run set.seed 1, 2, 3, and then we run this, we're creating an object called sample, it should be sample cars, but simple cars. And so we're taking that car data we just called in and we're piping it into a sample n function. And we know that n typically stands for sample size. So it's saying a sample of sample size 20. So now if I run this variable that I stored, I see that I have 20 rows, which I can see up here, 20 observations, and I have it for all 9 variables. So we took a sample of size 20 from this car data and we stored it in simple cars. Okay, so the point here is that we needed to use a function to get this random sample. It does not just when we, print out the first 100 observations from a data set in R, that is not a random sample. If we use select star in SQL, that is not a random sample. It is giving you the data based on some index that you may or may not even see. So you want to be really aware that when you are trying to take a sample, that you are specifying, you're using some special function that is letting you know that it is a sample. And so you can also, they're in SQL as well. If you're getting your data from SQL, when you're, when you get a job in data science, in the different flavors of SQL, it's a different, the name of the function might be different, but typically at the end of a query that's going to return, 100,000 rows or whatever. If I put sample 50,000, it'll just give me the 50,000 rows. So you'd have to Google and find out exactly what the name of that function is. But if you want a random sample, you have to be sure to make sure that you're using a function specifically that will provide you with a random sample, right? Because what can happen if I just take the first 100 rows in R? The way that the data is coming back to you, since it's not random, it could be often the index might be like subscriber ID. And so people with earlier, smaller number subscriber IDs are typically older customers. They've been here longer. And so that introduces bias, right? Because older customers are potentially going to have different behaviors than if I grabbed a representative sample that had a mix of newer and older customers. Okay, so sometimes a simple random sample isn't enough. So this specifically happens when you have, the business is going to sometimes care about variables that don't happen that frequently, right? Like you might be doing an analysis and maybe we have like 6 products or something, and very few people buy the 6th product, but they still want to understand what's happening in that 6th product. So we wouldn't want to do a simple random sample on the database, because if only 1% of people are buying that 6th product, well, then we might not get enough data in our sample to actually do an analysis of that 6th product. So then we could instead say, okay, we're going to take a sample of each product, and let's say we're going to sample 20,000 of each product, so that we know we have enough data to look at each product, right? Instead of just pulling directly from everybody, we're going to sample, basically doing the same thing, but we're going to sample within each product in this case, or in this example, it's a group. And this you want to have an idea of right ahead of time, because if you had taken a random sample and then later did a bunch of work and then found out that you didn't have all the data that you needed to give a clear picture, because let's say you only ended up with like 70 rows of data for product 6. Well, what can I do with 70 rows of data? I can't be confident that that's representative of the population of people who bought product 6. Okay, so, and we're able to do this in R as well. So again, because we are running this function again, this getting a sample, we again need to set a seed. The number in the seed doesn't matter. You can give it any number. You just want to make sure that if one of your colleagues is trying to rerun what it is that you've done, they're using the same seed so they can get the same results. But the number that you use in set seed doesn't matter. And so all I'm doing here, so in this case, we're still using the car data, but we're going to sample 10 of each transmission. So there's manual transmission and automatic transmission. So I'm just going to group by the transmission first and then take my sample. And so I'm still using this sample of size n function. Okay, and then I'm able to look at this. And we're not able to see all the variables, so let's use here. So we can see that we have 10 with automatic transmission and we have 10 rows with manual transmission, and that was set up by design. So the car data has 300 rows in it, and I said, okay, group the data by automatic and manual, and then give me 10 randomly chosen rows from each of those groups. Okay, and so Paul is asking, is there any way to include the transcript of the chat and Q&A on the website? We can get the recordings, but it would be helpful to also have the questions in chat that was discussed during the recording. So yeah, program support, would you mind putting the information in chat into a like Google Doc and putting it up on Canvas after class is over? Okay, so program support says they can do that. And then can you please give Danielle a panelist link? Okay. Okay, so this is our stratified random sample. And so while we're here, let's talk about testing and training splits. So we have this sample split function from the CA tools library. And so again, we're going to set a seed before we run any of this. And again, the number doesn't matter. And so I'm able to say, so a typical test training split is 70-30. So you want 70% in training and 30% in test. And so we're able to run the set seed so that it's reproducible. And this sample is going to give us back a Boolean for each row. So basically what it's saying is, right, so 70% of these should be true. And what that means is true, this is part of the 70%, and false is part of the 30%. And then all we do is say, okay, where the sample equals true, we filter the data. And so this way we're only keeping 70% of the data in train. And if we limit the rest of the data, if we filter the rest of the data and say we're going to assign all the falses to test, now we have a random 70-30 split of our data. So we just successfully split our data into two groups. Using the Boolean that was created by the sample split. Okay, and so we're able to look at, the test data and see, okay, it's just the data set. And we know that there was 301 rows here, and there's 91 rows in the test set. So it's not going to be perfectly, right? It's not going to be a perfect 70-30 split. And that's not what we expect. We expect roughly a 70-30 split because what it's doing is each row has a probability of 0.7 of being assigned to the training set, right? So it is possible, just like with, when we talk about the roulette and betting on black, yeah, we're going to hit black, like black should come up with probability 0.5. That doesn't mean that, it's going to go black, red, black, red, black, red, right? There's randomness here. And so with probability 0.7, each row is going, like it's generating a random number. And if that number is less than 0.7, mark it true. If it's greater than 0.7, mark it false, right? So it's generating a random number, and then based on that, it's going to assign the row. And so it's not going to be a perfect 70-30 split, right? Hi, Nathan. So A 70-30. Ooh. So 70-30 is a typical split because it's just been found to give people enough data to build and train their model, but also enough data in test to be able to understand the prediction accuracy. And so if you had a really small data set, you might want to do something like 50-50. You don't have to do 70-30. It's just become industry standard. Personally, I have lots of demos where I'll just choose a random, I'll just do 0.6 and 0.4 or whatever I'm feeling at the moment, depending on the number of variables that I'm going to have and the size of my data set. But there are people who sort of live and die by the 70-30. Like, just like you noticed, I changed this to be 0.7. I think I had 0.8 here when it came. And so it really comes down to, you know, when you're building a model, you need to have like at least 16 to 20 rows per each parameter you have, but that's more of a statistical way of looking at it. And often we have a lot of data, and so it doesn't actually matter. But someone with a smaller data set might consider the number of parameters that they're going to have in their model and their limited data and say, okay, well, if I need to think about the best way to break this up, like there's just like a lot of factors. No, Nathan, it's definitely not a hard and fast rule. And there are so many different scenarios and use cases that this is used for that, we could talk all day about like, well, if the size of your data set goes up or if the number of your parameters in your model goes up. But really, as long as you have enough sample size to know that you can analyze your results, and like you're going to have over 500 for each slice that you're making, so that like if you were to take a mean or run some analysis or whatever, you can trust a bit what the results are. That's fine. Oh, yeah. No, when we first opened this up, I had the 0.8 there. I put 80% in train and 20% in test, but I had just changed it to 0.7 real quick in lecture because 70-30 is sort of what you'll hear in blog posts. Okay, so let's get into, hold on, I'm just catching up on the chat. Okay, so random variables. So we're switching gears here. We're moving to the second and larger topic of today's discussion. And so we're going to be talking about random variables. So it's a function whose possible values are mapped to numerical outcomes of a random process. So you could imagine that if this was, rolling a die, right, then it would be 1, 2, 3, 4, 5, 6, because there's 6 outcomes. And this would be the total set of possible values, right? There'd be nothing missing there. It's complete. And so the thing is we sort of know that rolling a die has a you know, each number has a value of 1/6 probability, but you can imagine a scenario where we have X and this isn't a die, and each of these possible values have a different probability of occurrence, right? And so this is discrete, right? It's not continuous because it can only be 1, 2, 3, 4, or 5. And so we can write the total set as X equals the set 1, 2, 3, 4, 5. Random variables are typically denoted as X. They can be discrete or continuous. In this case, it is discrete. And so, you know, in the example that we're going to look at, it's that we have 5 different products on our website. People may buy 2 of the same product. So if I'm selling apples, bananas, cucumbers, people could buy 2 apples, right? But what we're really concerned with is how many different products people are buying. So how many people are buying a banana and an apple and a cucumber, right? So the random variable X can take the values 1, 2, 3, 4, or 5. So when somebody comes to the website before they purchase, we don't know how many products they're going to buy. And so the population here that we're talking about is of the people who buy something, right? Because the majority of the people who come to the website aren't even going to purchase something. A really healthy conversion rate for a website would be like 20% in e-commerce. So, right, so a possible value there could also be 0, but here we are saying for the people who come and purchase, this is the number of different items they purchased. Right, and so we can write out the probabilities, and it might look something like this. And so, you know, the majority of people who buy a product, they're probably only going to buy 1 product. But some people will buy 2 different products, and very few people will buy all 5 of the products. But if this was our random variable, right, and this was the probability distribution of this random variable. So the random variable maps X to 1, 2, 3, 4, or 5. And then these are the associated probabilities. And the rules for a probability distribution is that every single probability, right, because we know probabilities can't be negative. We also know they can't be greater than 1. So each probability has to be between 0 and 1, which these are. And then the sum of all the probabilities has to equal 1, and these do. So 0.7 plus 0.24 plus 0.03 plus 0.02 plus 0.01 sums up to 1. Okay, so this would be an example of a probability distribution function for a discrete random variable. And so this is going to sort of build up to the rest of the lecture if this seems a little like abstract. And so we can sort of look at the number of products purchased, even though it's the probability distribution, because it is discrete, we could also refer to this as the probability mass function. So if you see that in the literature anywhere, that is another name for it. So given that in a probability distribution, all the probabilities need to be between 0 and 1, and they need to sum up to 1. It's time for our poll. So which of the following would be a probability mass function? And so program support is going to put a poll up for this, and you guys can answer. All right, and I'll give you guys some time to do some calculations and cast a vote. And so only one of these is actually a probability mass function. So Laura, only one, you have to choose option 1, 2, or 3, and only one of them is a probability mass function. All right, guys, do you want to let me know in chat if you've had a chance to vote or if you're still working on it? Okay, guys, if you haven't voted yet, vote real quick, and program support, maybe give it 10 more seconds and then show the result. So Laura, you should have had a poll come up on your screen. All right, program support. How do we see the results? Because I don't see them, but it might be because I'm screen sharing. Oh, okay, wonderful. All right, so 38% of the class got it correct. The answer was option 1. And so, oh, okay, and this is because if we just came over here real quickly and said, okay, 0.1 times 1, right, is going to give us 0.1, and 2 times 0.1 is going to give us 0.2. So if we summed up 0.1 plus 0.2 plus 0.3 plus 0.4, we get 1. So if we used option 2 that has a 5 in there, it would have summed up to 1.5, which is greater than 1. And we know from these rules, right, that each probability has to be between 0 and 1, and that's why option 3 doesn't work. And then the sum of the probabilities has to equal 1. So 0.1 plus 0.2 plus 0.3 plus 0.4 equals 1. And so that makes it the correct response. Okay, so that was talking about the probability distribution function. And so now we're going to talk about the cumulative distribution function. And so discrete and continuous random variables, which we've just talked about. So, and we've only seen an example of a discrete random variable, but in the rest of lecture, we are going to talk about continuous random variables. They all have a cumulative, if you are a random variable, you have a cumulative distribution function. And so in our discrete example, the simpler example, all you need to do to get the cumulative distribution function is to sum up the previous probabilities with itself. And so here's a quick note on notation. So for the probability distribution or probability mass function, we were using the lowercase f of x. When we're talking about a cumulative distribution function, we use the capital F of x, right? And it's for the probability mass function, it was the probability that x equaled 1 was 0.74. And now we're going to be looking at the cumulative distribution function, that is the probability that x is less than or equal to x. So you notice that this visual was used because as we go to the right, we're monotonically increasing. So there's not going to be a dip anywhere. And so using the probability distribution that we have, we can calculate the probabilities of different scenarios occurring. And we can also calculate the cumulative distribution function. So we're not quite there yet, but so we know that the probability of x equaling 1 was 0.7. We knew that the probability that x equals 2 was 0.24. The probability that x is greater than 2 is the same as the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5. So that's the 0.03 plus 0.02 plus 0.01 gives us 0.06. Okay, and so another way that we could write that the probability x is greater than 2 is that it's also the same as 1, because probabilities all sum up to 1, minus the probability that x is less than or equal to 2, right? Because before x greater than 2, that starts at 3. So we want to make sure that we do the 1, the total probability, minus the probability that x equals 1 plus the probability that x equals 2. And you'll see that we get the same probability. So these two things are equivalent. The probability that x is greater than 2 equals the probability 1 minus the probability that x is less than or equal to 2. And so these two statements are equivalent here. And then the probability that x is between 3 and 4 would just be the probability that x equals 3 plus the probability that x equals 4. So 0.03 plus 0.02 equals 0.05. How are we doing, guys? So Josh, the easiest way to state the difference between the PMF and the CDF is that the CDF is really the integral of the PMF, right? So the PMF is the derivative of the CDF, if you're familiar with calculus. How many people here have had calculus? Could you just let me know in the, okay, Steve. Okay, Laura, you've had calculus. Perfect, perfect, perfect. Okay, so when I say that the relationship between the PDF and the CDF is that the CDF is the integration of the PMF, that resonates with some people, because that's the easiest way to describe the relationship. It's the area under the curve, right? And so in the discrete example, now if we wanted to, yes. So Subhash asked, so on the last formula, the probability of being between 3 and 4 is that the values equal 3 and 4. That's right, because there's no other values. So, right, we're saying X is less than or equal to 3. So it can be equal to 3. I mean, greater than or equal to 3, or it's less than or equal to 4. So it can be equal to both 3 or 4, and there's no numbers in between there because this is discrete. Right, Steve. So in yes, Francisco. And so we are a little bit more easy to see this here. So Josh, I don't think we can say it that way. Right. Well, because when we get to the continuous example, right, of course, a single point has no mass because a line has no mass. So we calculate the area under the curve. To get our probabilities utilizing, so this is a probability mass function, but there's two things going on here. The CDF itself would look like, whoop, and it would go up from here, right? Because it's the probabilities, it's the summation, it's the cumulative of all the stuff before it as well. And for continuous random variables, we also, with the discrete random variables, we were able to just sum up the probabilities at each point because we had a discrete number of points. But then when we're talking about continuous random variables, a line has no mass or width, so we need to integrate to get the probability that X is between two values, right? And we remember from the definition that is the definition of the CDF is the probability that X is less than or equal to X. So creating the CDF, or whether we're just calculating the probability for a range, it's the area under the curve, right? And that's also sort of signified by the fact that we're using a capital X here and a capital F here and a lowercase f here. Okay, so let's look at the yes, Louise. So that is a random variable X that maps to values 1, 2, 3, 4, and 5. And the probability distribution associated with that is that 1 is 0.7, 2 is 0.24, etc. But it's, you know, we're saying that it's a random variable X that maps this way. And so that's this X, right? So X is our random variable. And here in this case that we're working with, it takes 5 values, and each of those values in the set has an associated probability. Nope. So through our analysis, we found that in general, 70% of people buy one product, 24% of people buy 2 products. And yes, over time, these may change, but right, we do an analysis of the population, of the data that we have, and come up with, at that time point, what's the probability that somebody who buys from the site is going to purchase 1, 2, 3, 4, or 5 products. So we're not saying that it varies in this case, right? So over time, 6 months from now, if I was to look at this distribution, maybe it would have shifted slightly, and I'd have to say that there was like a new norm, right? Like people who come to the site now, you know, maybe we release a new product and we have 6 products and things change. So we're trying to get through it, Subhash. The CDF cannot have negative values. It's all positive. You're summing up positive probabilities. Where is it negative for X? So yeah, so you'll notice here that it's taking the value -1, but it's never below. This is the probabilities. So the probabilities are between 0 and 1. Yep. Yeah, so but it never goes below this 0. X can be -1, -2, -3, -4, -5, but X is not probabilities. Okay, perfect. Yep, sorry about that. Okay. So just sort of, so the idea, right, is that we've got a random variable, we've got a probability distribution function, and we've got a cumulative distribution function. Okay. And so don't worry about it too much, because like a deep understanding is not required to get through this. But we did want to introduce it so that when we start to talk about common probability distributions, we have an idea of what a probability distribution actually is and what it means. And so some of the very common probability distributions that we see occurring in, you know, natural phenomena are the Bernoulli, the binomial, the geometric, and the Poisson. And so those are discrete. And then with the continuous, there's the uniform, normal, students t, chi-squared, and exponential. So Poisson is count data, so counting things, which, you know, is again discrete, like counting items. Geometric, the example that I give is that, you know, women have a probability of 0.2 each month if they are trying to conceive a child. And, you know, if you've been trying to conceive for over a year and you are unsuccessful, then you would start seeking fertility treatments if that's the route that you wanted to go. And it's because that follows a geometric distribution, because the first month, you know, the probability is 0.2. And then you're looking at, well, the next month, okay, they say each month you have a probability of 0.2, but when I'm talking about the fact now that this is my second month, given that I didn't get pregnant the first month, my probability is reduced. And by the time you get to month 12, your probability has been reduced significantly to the point where, you know, it's time to think about getting additional help, because although, you know, within that month, it's like, yes, I have, you know, on average, people have a probability of 0.2, but in the 12th month, given that you had a probability of 0.2 the last 11 months, you are at that point quite unlikely to. And if you do the math out, it's really interesting that like the 1 year is the cutoff. So that's what the geometric distribution models. And again, that's discrete because we're talking about discrete months. I can count the months on my hand, right? It's not continuous. Binomial is discrete that approximates a normal. Bernoulli, we're going to look at a little bit more. Basically, it's that, you know, we're just going to look at a little bit more. It'll probably be more confusing if I just talk about it. Uniform is having the same probability across, but in a continuous way. So Bernoulli is the discrete, like I'm going to do a trial and it's going to have a probability of 0.7. But this would be, you know, 0.7 on an interval that was continuous. But of course, the area under the curve can only be 1, so it would only be 0.7 until, so the easiest way would be, you know, on the number line from 0 to 1, having okay. So from 0 to 2 on the number line, having a probability of 0.5, no matter where you are. And the area under that curve would be 1. So it sums up to 1. So it is a probability distribution function. And if we were to create the CDF for that, it would look like, you know, a straight diagonal line. Students T, we're going to talk about more chi-squared and exponential. We do not have time to talk about in this course, because the point of the material is we want to get to a place where you are going to be able to understand confidence intervals, statistical significance, which is why we care about these distributions, p-values, and this allows us to interpret machine learning output, or I guess, you know, linear regression isn't really machine learning, but it'll help us to interpret linear regression and logistic regression output, which is something that is covered in this course. So because of that, we're going to focus on the normal, students T, Bernoulli, and binomial distribution. There's way more distributions than what was even in this chart here. We could do a whole course on probability distributions, but we're just going to focus on the ones that we need to be successful in this course. Okay, also some definitions, right? A lot of these probability distributions are going to have a mean, they're going to have a variance, and then the square root of the variance is our standard deviation. And these numbers are going to allow us to put our confidence intervals together. And so let's go over to R and just look at, so the mean is the average, right? So it's the sum of things divided by the number of things you have. Variance is the dispersion. How far are we from the mean in general, right? And so the square root of the variance is what we use to talk about, we talk about standard deviations about the mean, and there are, did I get rid of the slide that had, oh, okay, so for the normal distribution, we know that in general, 68.2% of observations are within one standard deviation of the mean. We know that 95.4% are within two standard deviations of the mean. That's why 1.96 is so often our Z multiplier. It's because we're looking for 95% confidence intervals, 95% confidence, and 95.4% of observations are within two standard deviations of the mean. So that's why 2 and 1.96 are quite close. And then within 3 standard deviations of the mean, for normally distributed data, we expect to capture 99.6% of the observations, right? But so let's just quickly look at in R, I'm able to generate 5,000 observations. So I'm randomly generating this. That's like the theme of today, is randomly doing things. But so since I'm not setting seed, other people's will be slightly different to mine. So if you want to get the same exact answers, we can all just set a seed. Set seed 2, 3, 4. Okay, and so I am randomly generating 5,000 observations from a normal distribution, and I'm saying that the mean is 20 and the standard deviation is 4. Okay. We can look at a plot of this. So we see that it looks normally distributed. We see that bell curve, right? And so we're able to look at a summary table of the data, and we see that the mean and the median are very close, which is something that is true of the normal distribution. We expect the mean and the median to be very similar, but they often won't be perfect because this is a sample and we're not using the actual math function that was utilized. So in probability, right, if we had defined this function to be a mean of 20 and a standard deviation of 4, in probability the mean is 20. But here we actually took 5,000 observations, and we found that the mean of our observations is 19.993, and that was generated from a normal distribution with mean 20 and standard deviation 4. So it's very close, but it's not exact because this is statistics and there's uncertainty in our data, right? But so just to show you some of the functions that are in here so we can calculate the mean. And so this one in the summary table has been rounded a little bit, but so we can get the mean, we can get the median, because these are all stats that you're gonna wanna be able to calculate. So, and we can see that the mean is actually the sum of this data divided by the length of the data, right? Just like in the formula, we had the sum of x1 plus x2 plus x3 divided by n. N is the number of rows. And so the length of this normal data is the number of rows that we have. So you can see that. And you can see that the length is 5,000 because we had generated 5,000. Why does this say 50,000? This was for the histogram? Yeah, because normal data only has 5,000 in it. Right, so if we run this, we get the same number here that we had for the mean, because this is just another way of calculating the mean. To get the variance of this 5,000 sample we took, we can just use the var function. And we see that the variance is 14.76. And then the square root of the variance is what gives us the standard deviation. And so the standard deviation is 3.97, which is really close to the 4 we specified. But again, it's not perfect because we pulled this randomly. And so taking the square root of the variance is the same thing as using the built-in SD function for standard deviation. See, these are exactly the same. Okay, so one standard deviation about the mean is going to be going out for roughly 4 this way and 4 this way. And so this right here should contain 60-something% of the data. And then going out to, you know, another 4, we're going to, oh, nope, because that doesn't actually give us 95%. Because it's not a standard normal, so we'd have to standardize this first. And then we can do the same thing with the Bernoulli, but we'll wait on that. Okay, so we just looked at how to, so we see the mathematical formulas here, but we also saw how to implement the functions that can give us those results in our, based on our data. So we looked at that. So now let's talk about the normal distribution. So, right, we were talking about random variables x. So x can follow a normal random variable. And then the notation becomes this because it's a function of x, but it also has parameters mu for the mean and sigma for the standard deviation. So, right, so for the 68.2%, it has to be a standard normal. Francisco, this one has new at the beginning of it, and it was uploaded about 20 minutes, or it should have been uploaded about 20 minutes before lecture started. Did you download it a little early, or program support, you put this up, right? Okay, so this one was supposed to be put up before lecture. Program support, can you make sure that the code I sent through today makes it onto Canvas? Thank you. Okay. Okay, and so it's for a standard normal that the 68.2% of observations are within one standard deviation. And so that's a transformation that we can do by taking our values, subtracting them by the mean, and dividing by sigma. And so it's dividing by sigma that allows us to get into this place where, so we could transform our we could do the calculation with hours to get it to be a standard normal. But I would like to get to a point where we can open up for questions. And so this sort of does tie into some of the stuff around confidence intervals and stuff. So why don't we stop here, because this is a lot of material, and on Thursday we'll pick up from here. Yes, Steve. So one standard deviation is 68% of the values of a standard normal. So we'd need to standardize the normal. Okay, we already asked about that. So is it still up? Yeah, so this is, right? So I don't know if you've ever heard of a z-score or the z-multiplier of the 1.96 that gives us 95% of the probability between negative 1.96 and positive 1.96. But so basically, if we took each observation and subtracted it from 20, which is the mean, and divided by sigma, we could move our, here, let's just try and do it live. Okay, so we've got our normal data. Okay, so I'm going to create a standard normal. And that is going to be normal data minus 20 divided by 4. So now I've got 5,000 values that have all been transformed a bit, right? And all I did was subtract the mean and divide by the standard deviation. And so now I can plot my standard normal oh. You know what? I'm just gonna, Oh, because I had it named wrong here. Steen. Okay, there we go. Let's see if it'll let me do a plot instead. Nope, nope, that's not what I want. Okay, we'll go back to histogram. Okay, so now you can see that since we did this subtraction and then scaled it by the standard deviation, that it's now centered at 0, and 1 standard deviation brings us over to 1, and this is going to be from -1 to +1, and that is the 68.2% of our values. And then from -2 to 2 is going to be 95.4% of our values. And with 3, we find that we're, at that 99.6 place. So that was how we literally just subtracted the mean and scaled each of them by the standard deviation. And then that gave us these values instead, which give us those nice properties. Oh man, Danielle. Yeah, I know, right? So we're not talking about z-tests today, Francisco. This is a z multiplier, but the z-test is more towards hypothesis testing, which is a couple lectures from now. All right, so what kind of questions do we have, guys? We only have like 4 minutes left. So Subhash asked, can I make the 68% to 100% to stay in range? And I don't know what you mean by that. Oh, but yes, Francisco. So the price of the cars is not normally distributed, so I wouldn't use a z-test, and the sample size is small. There's only like 300 rows in that data. But yes, you could, if you took, I wanted to see the price of cars was statistically different by the type of transmission. You could use a statistical test to test that. I don't know off the top of my head that I'd use the z-test though. How can I restrict my values within a range like 16 to 24 and not dip to a 3? So you can't, if it's random, right? Like it happens with very low probability, but like you could get some like intense outliers randomly. And so you can choose to remove those from your data set, but they are part of the naturally occurring distribution. Oh, you're okay. You're in the middle of a science fair. Okay, so Francisco, so if you need help choosing a statistical test, hold on, I've got an article for that. So it's definitely going to depend on the size of the data and the structure, but so I have an article on choosing the correct statistic for your hypothesis test. Yeah, and so, I mean, there's a chance that your t-test is fine. Sometimes, and the data is not normally distributed, but I think in my example, I show how I used two different tests and they came out the same. So it's a lot of times you just want to be consistent too, but that there's a cheat sheet in there that will help you determine what's the best test statistic to use given what type of data you have and what it is you're measuring. Okay, Nathan. Danielle, do you know what that means? So the LMS is Canvas. Are you logged into Canvas? Is there a chance that you got signed out for some reason? Okay, program support, do you know if this week's assignment has been published yet? All right, guys. Well, it is after 12:30, so I do need to. If program support gets the new file in week 5's webinar codes. Yes, so that was sent before lecture and was supposed to go up, but they apparently haven't had a chance to do it yet. So thank you, guys. I know that this was a lot of material and Nathan, so Francisco was talking about the newer code for Module 5 to go along with the lecture. Program support has not mentioned whether or not they have released the homework for 5. Yeah, I'm sorry about that. All right, everyone. So I hope you have a wonderful couple of days. We are going to be meeting again on Thursday because this is such a heavy topic. So we are going to just dive right in and do some more probability and stats on Thursday. And then the following Tuesday, we'll be talking about hypothesis testing and what you need to look out for there. So, And even though there is 2 lectures this week, there's only 1 homework assignment, just so you're aware. So the assignment, once it's up, is the assignment for the whole week. And I will see you guys on Thursday, which isn't too far away. Okay. And Danielle is saying that office hours are on Monday and she hopes to see you guys there. All right. Awesome. So I will see you guys on Thursday. Thank you.